Okay, hello everyone. In a new video. In this one, we are going to explain a new chapter, which is chapter 6, which is the chapter of AC voltage and the second unit of electricity. So, before I start with section number 1, which is the AC voltage, let me consider the following two documents. In the first document, we have a device in which this device is fed by two batteries. This is the first battery and this is the second battery. So notice that in this case we have some indications, which means that the negative pole of the battery must be connected to this and the positive pole here must be connected here. And the same goes for the second battery. So the negative pole must be connected here and the positive pole must be connected here. In this case, we can deduce that the directions or the polarities of the batteries is important for the functioning of this device. And we have seen this previously. This is given by the DC voltage. Now, in the case of the second document, here we can see that this is the wall outlet, and here we have the wire or the plug of an electric device. And as you can notice that in this case we don't distinguish between the polarities of this device. So now this outlet is supplying a voltage, and in this case we are not distinguishing between the positive pole and the negative pole of the outlet. So we can connect this wire to the wall outlet in two ways, either in this way or the other way around. So in this case we are not distinguishing between the positive pole and the negative pole of the voltage source, and this is mainly known as the AC voltage. Then in chapters 3, 4 and 5 we have discussed in details the properties of a DC voltage source, and a symbol is given by this, in which this larger one is considered to be the positive pole and the smaller one is considered to be the negative pole. And when connected to a convenient closed circuit, an electric current will be directed from the positive pole to the negative pole. And we have seen the relation between U and I across ohmic conductors, as well as the electric power and some other properties. Now in this chapter we are going to discuss everything that we have discussed in the case of DC voltage, but as for the AC voltage. Then for this reason, let me start with section number 1, which is given by the AC voltage. Then as we have done in chapter 3, by starting with defining what is meant by DC voltage, now I will not discuss the electric circuit regarding the AC voltage. I will leave it for the other parts of this chapter. Now let me start directly by defining what is meant by an AC voltage. So an AC voltage so previously DC stands for, so we have discussed this previously, DC for direct current. Now in this case AC, C also stands for current, but A in this case stands for alternating. For this reason is an alternating voltage. By alternating here, I mean it's changing. So is an alternating voltage, which means, which varies with time and is alternately positive, and negative. Whereas in the case of DC voltage, a DC voltage, so let's recall that a DC voltage is constant with time. So here what I mean is that the alternating voltage changes with time, and it's alternately positive and negative. And here I mean that for a certain duration delta t, this pole is given by the positive pole and this is negative pole. For another duration, this is given by the negative pole and this is given by the positive pole. So it's alternately changing from positive to negative, negative to positive. For this reason, we don't distinguish between different poles. Now let me give some examples, some sources of AC voltage. Let me write down some. Sources of AC voltage. So for example, the power stations. We have EDL, Electricity of Lebanon. Also, we have low frequency generators. We have the alternator of a bicycle. And the wall outlet of the mains. Then all of these provide AC voltage. Now let's recall what are some examples of different sources that deliver DC voltage. We have different types of batteries. That are given by, for example, the AAA battery. Battery of cell phones. And the battery of a laptop, etc. Okay, so all of these are examples of DC voltage sources. Now, let me consider the following section, which is section number 2. So, different waveforms of a DC voltage source. So, different waveforms of a DC voltage. Now, in chapter 3, we have also seen how an oscilloscope can visualize the voltage. Now, let's recall that this is the screen of the oscilloscope, and in this case, the luminous line is displaced upward, which means that it's measuring a positive DC voltage. And here in this case, this is the screen of the oscilloscope, and because the luminous line is at the center of the screen, which means that this is a 0 DC voltage. And in this case, because the luminous line is displaced downward, which means it is measuring a negative DC voltage. So these are the different DC voltages that we have encountered in chapter 3. So, and we call them waveforms for the following reason that we will see in the next section, which is section number 3. Then let me write down. Different waveforms. Of an AC voltage. And now before we discuss, let me say the following, that whenever we have a graph, in physics always axes are labeled by physical quantities. So this is the x-axis and this is the y-axis. Okay, in this case, the x-axis is labeled by time and the y-axis is labeled by the voltage U. Similarly here, the x-axis is labeled by time and the y-axis is labeled by the voltage U. Similarly here, the x-axis is labeled by time and the y-axis is labeled by the voltage U. Also in this case, because this is the screen of the oscilloscope, this is labeled by time and this is labeled by the voltage U. For this reason here, we are saying that U is positive because it's displaced upward. Similarly here, this is time and this is the voltage U, which means this is 0 at the center. And this is time, so this is the voltage U because it's displaced downward, so U is negative. Now recall that we have referred for the DC voltage source, it is the one which is constant with respect to time. A DC voltage is constant with time, and as you can notice that this line has a constant value. For this reason, this is a constant voltage which is positive with respect to the time t. This is a constant voltage with respect to time t because it is 0, and this is a constant voltage with respect to time because it is negative. Sorry, it is negative because it's displaced downward, and it is constant because notice that for all instant time t, it has a fixed value which is given by, say for example, this is -2, then this is given by -2.6. Multiplied by the vertical sensitivity. Now, as for the following waveforms, first let me explain why they represent an AC voltage. Now, if we refer back to the definition of the AC voltage, we can notice that I have defined the AC voltage as the alternating voltage which varies with time, and it's alternately positive and negative. So it's first of all, it is changing with time and it is alternately positive and negative, okay? And here, as you can notice, because this is labeled by the time t and this is labeled by the voltage U, this is an alternating voltage because for several intervals the voltage is positive, because notice that in this case, this is the waveform is above the x-axis which is displaced upward, which means it is positive. For several intervals like these, so if you consider this one, this is displaced downward, which means that the voltage is negative. Then in this case, this is changing from positive value to negative value whenever the waveform is above the x-axis, or this axis which represents time, it is positive. Whenever it's below, it is negative. The same here, for this interval, the voltage U is positive because this is displaced upward. For this interval here, this is negative because it is displaced downward. For this interval here, it is positive, and for this interval here, this is negative. And because this luminous line is displaced upwards, so it is positive here. And as you can notice that it is alternatingly positive and negative. And the same goes here. This part is positive, this part is negative, this part is positive, this part is negative, so on and so forth. And for this reason, these different waveforms represent AC voltage source. Now, what do we call each of these waveforms? Because this shape has the shape of triangular shape, then we give it the following name: alternating triangular voltage. Now in this case we can complete the square in each case, and this is given by alternating square voltage, and in this case it has the shape of a wave, and this is given by the alternating sinusoidal voltage. Now we are mainly interested in the alternating sinusoidal voltage. For this reason, let's discuss the properties of the AC voltage and how to measure the voltage using the screen of the oscilloscope. Here we are only considering the sinusoidal voltage. So if we refer to this document, which represents the screen of the oscilloscope, this is the waveform, which is the curve that represents the variation of u as function of time. And as you can notice that this part is displaced upward, which means here the voltage is positive, here the voltage is negative, here the voltage is positive, here the voltage is negative, which means it's alternately positive and negative, which means it is an alternating voltage, and it has the shape of the sinusoidal. So what's the type of this voltage? This is simply given by AC sinusoidal voltage source. Now let's define X, which is the number of divisions between two consecutive peaks. Let me write down that X represents smallest number of divisions under which the voltage is reproduced identically. So here X represents the smallest number of divisions under which the voltage is reproduced identically. So if you consider this point and we need to count the number of divisions X, so we need to find another point in which the value of the voltage U is exactly the same, which is this point. Okay, so X represents the number of divisions between this point and this point. And if we count them, we have 1, 2, 3, 4. This one with this one will give us 5. So in this case, X is equal to 5 divisions. Okay, now also X can be counted from the lowest point on this waveform. So if you consider this point, we are trying to find another point in which the voltage is reproduced identically, which is this point. And now in this case, if you count the number of divisions between these two, we have 1, 2, 3, 4. This one with this one will give us 5. So in this case, as X is equal to 5 divisions. Moreover, we can count the number of divisions X, not from the peaks, but from the center. So if we choose this point, Now we will ignore this point because this point is not identical to this point, and we will choose this point. So always whenever we are counting from the center, we will skip a point. So choose a point, skip a point, then choose another point. In this case, the number of divisions is given by, so 0.5, 1.5, 2.5, 3.5, 4.5, and this is given by 0.5, which means that is 5. So usually we have three different ways in order to count the number of the value of x, either from two consecutive peaks or from the two lowest point, any two consecutive lowest points, or we choose a point from the center, skip a point, and we choose another point. In this case, the number of divisions is given by, if we count them, they will be given by 5. Now as for y, which is the number of divisions, under which the voltage reaches its maximum, so this is the maximum point reached by the curve. Then the number of divisions is simply given by 1, 2, 3. Now we can determine the value of y by considering any peak. So if you consider this peak, then the number of divisions in this case is also given by 1, 2, 3. Okay. Now why it's important to define the values of x and y, because now related to x and y we will extract the properties related to the AC voltage. Now let me start by the maximum voltage. Now in this case the maximum voltage is given by U max is equal to SV multiplied by Y. So this is the same formula that we have seen in the case of DC voltage source, and for any triangle in physics, for any formula in physics consisting of three variables, we can construct a triangle. So here, because we have multiplied, and U max will be at the top, SV and Y are at the bottom. Now let me recall what does each quantity represent. So U max is the maximum voltage or the amplitude of the AC voltage, and because this is a voltage, then the SI unit is given by capital V, which stands for volts. Now what about SV? SV, as we know, that it is the vertical sensitivity. And the SI unit of the vertical sensitivity is given by volts per division. The symbol is given by capital V divided by div, in which it stands for volts per division. Now as for Y, now Y is the number of divisions along the y-axis. and the SI unit of y is given by div, which stands for divisions. So here what I'm trying to say, if I want to give an example, so suppose that in this case the value of y is given by 3 divisions and the vertical sensitivity is given by 2 volts per division, then directly we can calculate the maximum voltage, which is given by U max is equal to SV multiplied by y. Then the value of SV is given by 2, the value of y is given by 3. Here we don't distinguish between y if it's positive or negative. Recall that in the case of the DC voltage, depending whether y is displaced upward or downward, the value of y is positive or negative. But in this case, in the case of AC voltage, always the value of y is considered to be positive, and this is given by 6 volts. Now, once we have calculated the maximum voltage, we can directly calculate another quantity which is given by the effective voltage. So in this case, the effective voltage is given by and for any formula in physics, we can construct a triangle. So here, because we have divide, the new effective will be at the bottom. This is U max and this is radical 2. And let me divide what does each quantity represent. So U effective is the effective voltage of the AC voltage. And its SI unit is given by capital V, which stands for volts. And U max is the maximum voltage or the amplitude of the AC voltage, and the SI unit of the voltage is given by V, which stands for volts. Now here also what I'm trying to say, because in the previous part we have determined that the maximum voltage is given by 6, then U effective can be calculated directly, which is 6 divided by radical 2, and we can plug this on the calculator. Now this is it for the voltage regarding the value of y, which represents the number of divisions along the y-axis. Now as for the x-axis, we can define also another quantities. Let me define the period So let me say that the period capital T is given by VB multiplied by X. What does each quantity represent? Okay, before, let me construct the triangle. So here, because we have multiplied and the period will be at the top, this is VB, this is X. And let me say where capital T is the period of the AC voltage, which is given by capital V, so period for sure it is time, which is given by seconds, the SI unit of time. VB is the time base, or also known as the horizontal sensitivity. And its SI unit is given by seconds per division, which stands for seconds per division. Also, sometimes this VB is denoted by SH, similar to SV, because this is the horizontal sensitivity, it's denoted by SH. And finally, what does X represent? We have defined X at the top. Let me write it here. X is the number of divisions along the x-axis. And the SI unit of X is given by div, which stands for divisions. Now VB is usually given, suppose that VB in this case given by 2 milliseconds per division, and we know that millisecond is not the SI unit of time. In order to convert from milliseconds to seconds, we divide by 1000, so this is given by 0.002 seconds per division. And in this case, the value of X we have calculated previously, it's given by 5 divisions. Then the period T is given by X multiplied by VB, which is equal to 5 multiplied by 0.002 seconds, which is equal to 0.01 seconds. Okay, so knowing the value of X that can be determined from the waveform and VB is given, one can directly determine the value of the period T. And now after we have determined the period T using the waveform, we can deduce another quantity which is given the frequency f. Then the frequency is given by so also for this formula we can construct the triangle. So here, because we have divide and the frequency will be here, the period here, and this is 1. And let me say where f is the frequency of the AC voltage, and the SI unit of the frequency is given by Hz, which stands for Hertz. And as for the period T, we have discussed this previously, is the period of the AC voltage. And the period is given by seconds. It's SI unit. Okay, so why we talk about the frequency and the period in this case? What's the period? The period is the time taken for the voltage to repeat itself. And recall that X was given by the number of divisions in order for the voltage to repeat itself. For this, we can define the period. The period is the time taken for which the voltage to repeat itself, whereas the frequency is the number of repetitions that the voltage perform in 1 second. Okay, so later we will discuss more what is meant by the period and the frequency. So now let's take them as follows. And here I want to mention something also, that this rule here, this formula here, only holds for the sinusoidal voltage. Okay, it doesn't work for the square voltage or even for the rectangular, or sorry, triangular. Okay, so it doesn't work for the square or the triangular. Now we have 4 formulas to memorize, and they are given by the following: that U max is equal to SV multiplied by Y. After that, we can deduce U effective, which is given by UM divided by radical 2. Now the period is given by VB multiplied by X. Also, this is written as T is equal to SH multiplied by X. After we determine the period, we can deduce the frequency, which is given by 1 over the period. Okay, and now let me consider the following exercise as a direct application on the properties of the AC voltage source. Now notice that in each of the following documents, okay, before I start, I will ignore document 4 because there is something wrong in this document. As for documents 1 and 2, 1, 2 and 3, all of these represent alternating voltages. Why? Because they are positive and negative, alternately positive and negative, and in particular they are alternating sinusoidal voltage, because the shape of the curve in each of the following cases, it is sinusoidal. So exercise 1, they are telling me documents 1, 2 and 3 represent the waveforms of a voltage U delivered by different generator. In each case, let me start by number 1. So for each document, we need to repeat the following questions. Then let me start with document 1. In 1.1, we need to determine the maximum voltage. So before I start, the trick in solving such type of exercises is to write the values of X and Y before we start, okay? So what does X? X is the number of divisions along the X-axis between 2 consecutive peaks. And in this case, the value of X is given by 2 divisions. Whereas the value of Y, Y is the maximum displacement given by this curve. So it is the number of divisions from the center to the peak, and in this case is given by 1, 2, and 3. Now after we have determined the values of X and Y, we can directly apply the formula. We are interested in determining the maximum voltage. Then UM is given by SV multiplied by Y. Here we don't have any law, we can directly apply the formula, but before replacing we need to write the formula in terms of variables. Now the value of SV is indicated here, which is given by 80. Now notice that also VB, before referring to VB. Now the value of Y is given by 3. And plugging this on the calculator, then the value of maximum voltage is given by 240. Since SV and Y, both of them are expressed in the SI, so the value of UM will be in the SI, which is volts. Then UM in this case is given by 240 volts. Now as for part 1.2, they are telling me the period T. So the period by definition is given by VB multiplied by X. Now here VB is given by 3 milliseconds. It must be per division. So VB is equal to 3 milliseconds per division, knowing that milliseconds is not the unit of time. In order to convert from milliseconds to seconds, we need to divide by 1000. Then 3 divided by 1000, this is given by 0.003 seconds per division. Now the value of VB is given by 0.003 and the value of X is given by 2. Plugging this on the calculator, then the value of the period is given by 0.003. 0.006 seconds. So the value of the period is given by 0.00 seconds in the SI. Now after that, in number 2, for the same document 1, we need to deduce the effective voltage, and by deduce it means that we need to use the previous parts. In the previous parts we have determined UM. We know that U effective and UM are related via the following formula. U effective is equal to UM divided by square root of 2. In this case the value of UM is given by 240. And the square root of 2 is the square root of 2. Now plugging this fraction on the calculator, then the value of the effective voltage is given by 169.71. Since this is expressed in the SI, which is volts, and this is expressed, so U effective will be expressed in the SI, which is volts. Then U effective is given by 169.71 volts. Now in the same manner they are telling me to deduce the frequency F, and we know that the frequency and the period are related via the following formula. So the frequency is equal to 1 of the period. Now the value of the period is given by this. Now plugging this fraction on the calculator, then the value of the frequency is given by 166.67 Hertz. Then the frequency is given by 166.67 Hertz. So this is it for document 1. Now let me proceed to document 2. Now also the trick in solving such type of exercises, as we said previously, if directly to determine the values of x and y. So the value of x is determined by 2 consecutive peaks, which is given by 1, 2, 3. And the value of y is given by the number of divisions from the center to the maximum point reached by the curve, which is 1, 2. And let me also directly to write the values of SV and VB. So notice that here SV and VB are not indicated in this manner, but notice that here they are telling me that each one division corresponds to 110 volts, which means that SV is equal to 110 volts per division, because always this is the vertical, so this is the vertical, which means this is SV. Now as for SH, which is VB, notice that in this case VB is equal to 5 milliseconds, and in order to convert from milliseconds to seconds we divide by 1000, which is the SI unit of time. So in this case VB is directly given by 0.005 seconds per division. After doing so, now we are ready directly to answer each of the following questions. Let's start by 1.1. They are telling me determine UM. So UM is given by SV multiplied by Y. The value of SV in this case is given by 110. And the value of Y is given by 2. So plugging this on the calculator, then the value of UM is given by 220 volts. So UM is equal to 220 volts. Now as for part 1.2, they are telling me to calculate the period, which is given by VB multiplied by X. The value of VB is given by that. And the value of X is given by 3. Now plugging this expression on the calculator, then it's given by, because both VB and X are expressed in the SI, so the value of the period will be in the SI, which is seconds. So the period is given by this. So we have extracted these values from the given and using the waveform. Now we are ready to deduce the effective voltage. Which is given by definition UM divided by radical 2. The value of UM is given by 220. And divided by radical 2, then plugging this fraction on the calculator, then it's given by 155.56 volts. So the effective voltage is given by now also one can deduce the frequency from the period. So the frequency is given by 1 over the period, which is equal to 1 divided by 0.015. Plugging this expression on the calculator, then it's given by 66.67. Because the period is expressed in the SI, then F will be expressed in the SI, which is Hertz. Then F is equal to 66.67 Hertz. So as you can notice that whenever a waveform is given and its scale is also given in the document, then one can directly determine the values of UM and the period. And after determining UM and the period, from UM one can deduce the effective voltage, and from the period one can deduce directly the frequency, which is given by F. Then this is it for document 2. Now let me proceed to document 3. Then the trick in solving such type of exercises is to label the values of X and Y before we proceed, and to extract the vertical sensitivity and the horizontal sensitivity, or the VB, from the scale. So notice that in this case we don't have any two peaks in order to determine the value of X, but this can be done by choosing points from the center. So let's choose this point, skip a point, choose this point, and in this case the number of divisions is given by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And here let me say the following. So notice that in each of the following documents, the screen of the oscilloscope has the same size, in a sense that along the y-axis, so if we take any quadrant, if we consider this quadrant, always the number of divisions from here to here is given by 5, and from here to here is given by 4. What do I mean? The size of the screen of the oscilloscope along the x-axis maximum is given by 10 divisions, and along the y-axis is given by 8 divisions. Okay. Similarly here, if you count, this is 1, 2, 3, 4, 5, 6, 7, 8. So 8 divisions along the y-axis, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 divisions along the x-axis. Similarly here we have 1, 2, 3, 4, 5, 6, 7, 8. 8 divisions along the y-axis and 10 divisions along the x-axis. Notice that this waveform displaces all the screen of the oscilloscope, which has a maximum value of X, which is given by 10 divisions. As for Y, here, notice that, okay, so this is 3. The second subdivision is given by 3.2, and the first subdivision is given by 3.2, and the second subdivision is given by 3.4. This dotted line is to show that the maximum point reached by the curve is not 3.2 and not 3.4, but rather the point which is between 3.2 and 3.4, which is given by 3.3. So the value of Y is given by 3.3 divisions. Now as for the vertical sensitivity, this is the vertical. Notice that here they are telling me each division corresponds to 100 volts, which means that SV is equal to 100 volts per division. As for the horizontal sensitivity, which is given by VB, is given by 1 millisecond. From milliseconds to second, we need to divide by 1000. So this is given by 0.001 seconds per division. Now after we have extracted the values of x, y, SV and VB, the problem is solved. Why? So let me say 1.1. What is the maximum voltage UM, which is given by SV multiplied by Y? We always start by writing the proper formula. The value of SV is given by 100 and the value of Y is given by 3.3. Plugging this on the calculator, then the value of the maximum voltage is given by 330 volts because everything is expressed in the SI. Now directly also from the graph we can deduce the period T, which is given by VB multiplied by X. The value of VB in the SI is given by 0.01001 and the value of X eventually is given by 10. Plugging this on the calculator, then the value of the period in the SI is given by 0.1 second. Then the period T is given by 0.01 seconds. Now in number 2, they are telling me and deduce, and by deduce it means that we need this previous part. We have determined UM effective can be deduced by UM because it's given by U effective is equal to UM divided by square root of 2. The value of UM is given by 330. So plugging this fraction on the calculator, then it's given by 233.34. 0.35 volts. Then the effective voltage is given by 233.35 volts. And now in 2.2 we need to determine the frequency, and this can be deduced from the period because the frequency is given by 1 over the period. Then 1 divided by 0.01. Plugging this on the calculator, then the value of f is given by 100 because the period is expressed in the SI, so the value of f will be in the SI, which is hertz. Then f is equal to 100 hertz. So this is it for this exercise and this video. In the next part we'll complete explanation of this chapter.